Welcome back, focused learners. I'm absolutely thrilled to have you here for another explainer. Today, we're tracing a really fascinating journey through the history of blockchain technology. We're going to look at the ideological rifts that defined the early days of crypto, how those networks eventually evolved to offer some incredible new utilities, and finally, we'll examine the actual, physical, real-world cost of securing these digital ecosystems. It's a story about the evolution of proof, purpose, and the future of decentralized tech, starting from a massive network split back in 2017, all the way to today's innovations in smart contracts and environmental sustainability. Okay, let's dive right into this. To understand where we are today, we really have to travel back to 2016. Bitcoin was experiencing explosive growth, but it had a massive structural bottleneck. The network's block size was strictly hard-capped at just 1 megabyte. Because of that limit, the entire global network could only process about 7 transactions per second. So as demand skyrocketed, the system basically jammed. Users were facing massive delays, and transaction fees became completely unmanageable for everyday use. Sometimes you literally had to wait hours just to see your transfer go through. This crisis ended up forcing a massive wedge right down the middle of the Bitcoin community. The community fractured into 2 distinct ideological camps, and it's absolutely crucial we look at both impartially. On one side, you had the small blockers. They firmly believed that increasing the block size would require too much computing power. Their fear was that this would push out smaller, independent miners and hand control of the network over to massive corporations. So to preserve decentralization, they wanted to keep the base chain small and push excess activity to off-chain solutions like the Lightning Network, basically treating Bitcoin more like digital gold. On the other side, you had the big blockers. They argued that Bitcoin was always meant to be everyday digital cash. They simply wanted to raise the block size to accommodate more transactions directly on the chain, driving fees down and prioritizing fast, cheap payments. Well, the tipping point finally arrived in 2017 when the Bitcoin network activated an update called Segregated Witness, or SegWit. The big blockers completely rejected this, arguing it just didn't solve the fundamental scaling issue. So, on August 1st, 2017, exactly at block 478558, they executed a hard fork. This is such a fascinating concept because it proves that in crypto, if a community reaches an unresolvable disagreement, they don't have to compromise. There's no way. They can just rewrite the software rules, split the chain, and go their own separate way. The aftermath of that was immediate. Anyone holding Bitcoin at that specific block suddenly owned an equal amount of a brand new currency, Bitcoin Cash. These two networks share the exact same history prior to the split, but their futures? Completely separate. Bitcoin stayed the course as a secure store of value, and it's still processing around 7 transactions per second today. Bitcoin Cash, however, immediately scaled its blocks up to 8 megabytes, and later all the way to 32 megabytes. By doing this, Bitcoin Cash achieved its vision of acting as digital cash, comfortably handling over 100 transactions per second with incredibly low fees. Section 1. Expanding blockchain utility. Beyond simple transactions. So, what happens when a network wants to be more than just cash? That exact drive for utility brings us to an incredible innovation on the Bitcoin Cash network called cash tokens. This is a built-in, optional feature that lets any person, organization, or decentralized app issue their own uncounterfeitable digital assets. And what's really amazing here is the efficiency. Because of how Bitcoin Cash scales, cash tokens preserve the network's massively parallel performance. We're talking about a network capable of processing a staggering 25,000 transactions per second on modest, everyday hardware from 2020. Millions of users can interact with these decentralized apps without transaction fees suddenly spiking. What's really fascinating about this is how cash tokens actually handle different asset types to build these complex applications. Fungible tokens are your standard assets. Think stablecoins, voting shares, or loyalty points, where every unit is exactly the same as the next. But the non-fungible tokens, or NFTs, operate a bit differently here. In the cash token ecosystem, NFTs act as unique, authenticated messages. They uniquely allow smart contracts to call or interact with other contracts in a way that is completely impersonation-proof. This is the foundational building block that unlocks incredibly complex, decentralized applications right there on the Bitcoin Cash network. Now, this push for massive decentralized utility definitely isn't limited to Bitcoin Cash. Over on the Tron network, the drive for expansive utility led to a strategic integration with the graph, specifically utilizing a really powerful streaming product called Substreams, which is built by a team called Streaming Fast. This integration is essentially all about data accessibility. Tron handles a huge volume of transactions, right? And Substreams provides developers with an instant, real-time fire hose of blockchain data. We're talking live wallet activity, token swaps, and real-time total value locked. This directly empowers top-Tron protocols like JustLend and SunSwap, simply because they no longer need to build and maintain their own custom backend infrastructure just to track this data. Plus, and this is a real game changer, it features AI-ready endpoints that streamline how AI agents access balances and prices. It literally reduces developer integration time from weeks down to mere minutes. Section 2, the cost of consensus. How are these networks scaling their energy footprints? We've built these incredible high-utility networks, but what is the physical world sustainability cost of all this digital utility? To answer that, we turn to this really eye-opening June 2025 disclosure report. It was provided by Crypto Risk Metrics for a major asset service provider called 360T. And it's vital to note, this isn't just a casual environmental study. Providing these sustainability indicators is a strict regulatory requirement in Europe under the MiCAR framework. That's the Markets in Crypto Assets regulation. It basically forces these networks to transparently report their climate impact. Now, what's really interesting here is the sheer scale. At the very top, Bitcoin is consuming an astronomical 197 billion kilowatt hours annually. To put that into perspective, it's massive. But as we move down the list to networks utilizing proof of stake or other modern consensus mechanisms, that consumption absolutely plummets from the billions down to the mere millions, and in Cardano's case, well under a million. Let's break down exactly why this huge discrepancy exists. Bitcoin's immense energy hunger is a direct result of its consensus mechanism, proof of work. In this system, security is maintained by specialized computers called miners. These miners continuously race against each other to solve incredibly complex cryptographic puzzles using the SH256 hashing algorithm. It is essentially a brute force computational lottery designed to produce a new block every 10 minutes, and it requires vast amounts of electricity just to run and cool all that hardware. And the environmental results of that computational lottery? It's pretty sobering. According to the MiCAR report, Bitcoin generates over 81.5 million tons of Scope 2 greenhouse gas emissions annually. That is an incredibly heavy physical toll placed on the environment simply to maintain the network's decentralized security and keep transactions orderly. So the crucial point to understand is that while consensus algorithms might be identical, the network size and implementation change the footprint drastically. Bitcoin Cash uses the exact same SHA-256 proof-of-work algorithm as Bitcoin. However, because of differing network scale and hardware distribution, its emissions sit much lower, at about 318,868 tons of CO2e. Furthermore, the Bitcoin Cash ecosystem has actively explored utility through sidechains like Smart BCH, which actually uses a hybrid validator model to offer smart contract capabilities without drastically inflating the energy requirements of the main chain. To solve this energy dilemma entirely, other networks have built completely different architectures designed for ultra-efficiency. Solana, for example, uses a highly unique combination of proof of stake and proof of history, which kind of acts like a cryptographic clock to sequence transactions instantly. Ethereum, meanwhile, famously executed the merge in 2022, transitioning its entire network to a proof of stake system called Casper FFG. The environmental advantage here is profound. Proof of stake completely replaces energy-hungry miners with validators. Instead of burning electricity to secure the network, validators lock up capital. On Ethereum, you stake a minimum of 32 ETH. This staked cryptocurrency acts as economic collateral. If a validator behaves honestly, they earn rewards, but if they act maliciously, they suffer slashing, meaning their staked collateral is destroyed. By replacing electrical power with economic power, Ethereum dropped its annual emissions down to an astonishing 795 tons of CO2e. And we see this efficiency perfected in protocols like Cardano. Cardano utilizes the Ouroboros proof-of-stake mechanism. Here, slot leaders are selected to validate blocks based on the amount of ADA delegated to them by the community, rather than solving mathematical puzzles. Because there is virtually no competitive computation happening at all, Cardano achieves an incredibly low environmental footprint of just 273 tons of CO2e annually. It makes it highly sustainable while still remaining globally distributed. So this brings us to a profound crossroad for the entire industry. We've seen communities literally fracture over block sizes just to chase utility. We've seen innovations like cash tokens and substreams completely push the limits of what decentralized data can do. And we've seen these stark environmental realities of maintaining these networks, forcing a pivot toward energy-efficient consensus models. So I leave you with this to consider. As we step into the next decade of blockchain technology, which of these pillars, decentralization, utility, or sustainability, will ultimately define the networks that survive? Thank you so much for learning with me today, and I'll catch you in the next explainer.